It's my great pleasure to introduce our colloquium speaker today, Naftali Tishby, who's on a world tour, or at least a North American tour, and he's kind enough to stop by Perimeter for this colloquium. Like many, I think, people who work on machine learning and deep learning, Tali's a real renaissance man, but he's a physicist by training. He wanted me to emphasize that. He told me yesterday his first love was astrophysics, and then he's smart enough for his PhD, and I looked at nonlinear dynamics and statistical mechanics, and went on to postdocs at MIT and Bell Labs, is that right, before finding his way back to Hebrew University in Jerusalem as a faculty member. And so, like I say, Tali's a renaissance man. He works on physics and computer science, and as you can see, he's a chair in the Center for Brain Sciences, and he's most recently become very, very famous for the work he's going to talk about today, which is on the information bottleneck, which is a theoretical sort of foundations of deep learning. So let's welcome Tali.
Thank you very much, Roger, for the invitation and introduction. I'm really happy to be here. I mean, this is my last station before coming back home after about 8 weeks in the States, but it's looks like a very fun place. I'll be happy to come back again. So as was said, I mean, I'm really a physicist. I was always a physicist. The fact that physics is actually useful for other things is, I'm sure you all know that. But theoretical physics in particular is merging or coming into these fundamental questions that we face in machine learning, in particular in this aspect of deep learning, which is, as you know, neural networks that essentially emerge from an attempt to mimic the brain quite early on in the 40s already, where people suggested a computational model of the neuron, what we now call the McCulloch-Pitts neuron, which is essentially, so neurons tend to connect with other neurons and in order to process information, and essentially we can model them in a very crude way, in a very physics-like way, by just a dot product of weights by the inputs to this neuron and some sort of nonlinearity, like a threshold function, a sine function, or a sigmoid function at the end. This is what we call the McCulloch-Pitts neuron. And it was already in the 50s that this was suggested as some sort of a pattern recognition device by Frank Rosenblatt, actually. In 59, he wrote a nice book called The Neurodynamics of Pattern Recognition, something like this, and which essentially suggested the same model that we're using now, multi-layer neural network or multi-layer perceptrons. And this was essentially rejected as a good idea already in the 60s and 70s by his colleagues at MIT, Marvin Minsky and Frank Papert, and eventually came back in the 80s in this new connectionist age when I started to join this story with the discovery of backpropagation, which is essentially the chain rule of derivatives, which allows us to essentially train deeper layer by essentially taking the derivative of the error from the first layer to the deeper layers by the only assumption there is that you somehow can detect derivatives of this nonlinearity. So you move from a sine function to something smoother than a sine function, like a sigmoid function, and you can already take derivatives and move it backward. And this was enough to beginning this venture of training deep neural networks, not yet deep, I mean, few layers neural networks. And in the 80s, we actually thought that few layers, 1 or 2 layers, hidden layers, are sufficient because there are some theorems that tell us that we can approximate any function with one hidden layer neural network, as long as the number of layers there and neurons there is large enough. Now we know that this was a very theoretical result in the sense that in order to actually approximate any function, you need the number of neurons in this hidden layer to be essentially exponential in the size of the input, which means that also the number of parameters is very, very large, and this never turned out into a practical thing. So even in the 80s, in the first appearance of those neural networks, people are already working with several layers, and but this went down again through the work on, at least from the machine learning center, through the discoveries or the ideas of Vladimir Vapnik with support vector machines and kernel methods, some of you may have heard about it, which are essentially some sort of neural networks. But the big surprise came in the late 2000s, where essentially the same group of people like Jan LeCun and Jeff Hinton and a few others started to train those networks in a slightly different version, where they have many layers connected to each other, as in this picture. And essentially, not only the number of layers grew up by essentially an order or two orders of magnitude, from few to tens and hundreds, or even thousands, but the size of the problem in terms of the size of the input really grew up from a few hundreds to millions, or more than millions, in terms of number of variables that you see in the initial layer. And these two changes in the story, the number of layers and the number of size of the input, really changed the picture completely, in my opinion, and brought us back to ideas that I and many others have been playing with in the late 80s, which we call then the statistical physics of neural networks. And statistical physics of neural networks were essentially invented by taking methods from statistical mechanics, from the essentially statistical physics of disordered systems like spin glasses, and applying them to analyzing the weights and neurons in very large networks. But what we did in the 80s, and even this was very hard in terms of the power of calculation we had to do, was essentially applying a spin glass-like models to one layer, or sometimes two layers neural network. But the philosophy of this approach was that taking the thermodynamic limit, I mean, thinking about very large problems, is actually giving us the typical behavior of the problem. And we discovered very interesting phenomena already there, like phase transitions in the learning behavior, I mean, sudden jumps in the arrows, or all sorts of other physics-like phenomena, which we thought are very interesting, but were completely ignored by the machine learning community. And the irony is that these days, when we start to talk about very large problems again, and they are extremely successful, I mean, they essentially revolutionize fields like computer vision, speech recognition, computational biology, essentially data analysis in anything that you can think of, from control to language to signal processing, whatever. And these networks are obviously becoming very important apparatus, a machine for data analysis, but they tell us a lot more than that. But so the philosophy of statistical physics that was ignored since the early 90s, essentially, is coming back. And for people like me who've been there, and this is a renaissance of our own ideas. Now, it's really becoming a puzzle. I mean, one of the major puzzles in maybe the last 10 years, why those systems, which are huge number of parameters, but actually very simple conceptually. I mean, just layer by layer of processing with some connections, which are some sort of parameters of the models, huge number of parameters. I'm talking about 100 millions or even billions of parameters today. Why such big parametric models, other than just brute force, are capable of generalizing and capturing so well the properties of the problem? And what I argue is that we are beginning to have some sort of an understanding. I don't want to call it a theory yet. You know, physics theory is something important, but it's understanding in the sense that we believe that there are three different ingredients or different components to the problem which really play together in a very interesting way. The first one is more for computer scientists. I'm not going to talk too much about it. We have to rethink the basics of machine learning theory, or statistical learning theory. And instead, especially the way we bound the error, the generalization error, as a function of the training sample size. And I actually argue that we need really to rotate the whole thinking from what we call worst case distribution independent bounds, which are problem independent bound, but very sensitive to the algorithm that you are using, which we call the hypothesis class, to something else, which I call the input compression bounds, essentially rotating from the distribution independent bound to algorithm independent bounds, to things which are independent of the machine, but depends very strongly on the problem. This is, again, going back essentially to the ideas of statistical physics from the 90s. And this turns out to be an interesting twist, because it gives us, essentially it turns those useless bounds that we now have in machine learning for deep learning, useless in the sense that they depend heavily on what we call the expressivity of how many functions you can actually implement by those networks, which is huge, to something much more practical, which is data dependent, but it's a lot more realistic. And the other thing that happens is that we are talking about large-scale problems. So large-scale problems, as I said before, allow us to think about things like the thermodynamic limits, or like things that physicists are used all over the place. I mean, for a very large problem, we can do this asymptotic type of analysis and essentially talk only about the typical behavior of the problem. And the typical behavior of the problem tend to concentrate. I mean, we have this Gibbs-like distributions, which are essentially concentrate of very, very specific behavior. So the worst case and the typical case become very similar. But of course, there's always a small probability of having a very non-typical behavior. I don't care about those. I care about the bulk of the systems. And this brings us back to statistical physics or to information theory, which is very similar in its philosophy in terms of the ability to deal with typical behavior. And in particular, we have this property which we call self-averaging in physics sometimes, that quantities tend to concentrate in the distribution. And the quantities, that's what we call good order parameters in physics. I mean, those things which, when the problem becomes large, they become very sharp. And these are precisely the objects that we want to characterize here. So the spirit of this flavor of typical systems is precisely for physicists. And of course, the other thing that we realize now is that talking about deep parameters of the network, which are the best or the true parameters, is complete nonsense, because in these huge models, there are essentially infinitely many optimal representations. So we have to think about a way, not the way, to find one of those optimal configurations. And again, this has to do with the right choice of the order parameters of the problem. The last and probably the most interesting part of the story goes back to the properties of the way these networks are actually trained today. Now, I know that there's a lot of interest here in machine learning, both from what I call the application side. I mean, use machine learning to do computational physics very well, or to solve physics problems. But there's actually a fundamental science of machine learning in the sense that those systems are interesting enough on their own in the physics of what happens in the machine learning, and that's essentially what I'm looking at. I mean, as physical systems, they have a lot of interesting properties. And of course, this is related to our understanding, to our interest in biological systems like the brain, or in computational or in information processing in other whatever systems. Of course, those that talk about cosmology or I don't know, high energy physics can relate it to many different things. I mean, not necessarily biological systems, but it's information processing in general. What's going on here? And in our case, there's something very peculiar in the way those networks are trained by something which we call stochastic gradient descent, which is really a very stupid algorithm. I mean, you have an energy surface, which is essentially the training error of the error on the examples that you show the machine, which can be a very complicated function. And essentially, you start with some random initial conditions by initializing the weights with some randomly somehow. And then you calculate the derivative with respect to every one of the parameters of the network of this error function. And you move more or less in the direction, you do a small change in the weights in the direction of that minimize the error, the direction of the minus gradient of the error. Now, this is more or less the first and most basic optimization algorithm you can think of. But we don't even do this due to all sorts of computational reasons. We calculate an approximate to this gradient, which by essentially dividing our data into small pieces, which we call mini batches. And those mini batches are giving us some sort of a noisy version of the gradient. And this is what we call stochastic gradient descent. Now, I argue that at least one of the reasons those neural networks work so well is that this particular algorithm, this particular stupid algorithm, is actually very smart in a different way than what we used to think, because it's actually using this stochasticity, this variability of the gradients, in order to generalize well. So, okay. So this is the introduction. I'm going to skip some of the, I just want to relate to some, to my work, as was mentioned earlier, I mean, it appeared about last year as a very short conference paper full of typos and full of other things, but this paper was, of course, rejected from the two main computer science conferences, ICML and NIPS, but somehow, especially mainly due to my talks somewhere, it got very famous, and so it's a very funny situation. I'm actually talking about a paper that was not really accepted anywhere, but it became famous because some people listened to me talking about it and decided it is important. And since then, I get invitations all over the place. But the paper is still under revision, as far as I'm concerned. And actually, I learn a lot from the questions that I get during this tour and everywhere, especially some very smart people here. So I just want to argue, although this maybe is too early in this topic, because most of you don't know what I'm talking about, but the kind of criticism we get is that we don't estimate the information correctly. I'll tell you more about it. I just want to give one answer to this. We don't need to estimate information for anything that we say in terms of, we have a theoretical argument behind it. The pictures that I'm going to show you are illustrations, they're not the theory. The other issue is that you don't need to compress the representation. This again will become clear soon. These are actually the results of the arguments of two very interesting papers in the coming conference next week. ICLEAR, the information, International Conference on Representation Learning, or something like this, which is essentially in Vancouver, and unfortunately I'm not going to be there. And there's another set of criticism only directly to our work. So one came from Harvard, the other one came from some other group, which is essentially called RevNets, or reversible neural networks, which are essentially a different algorithm, completely different algorithm, although they're using SGD to train some subsets of this system, but it is essentially a Hamiltonian time reversible system, or area preserving, measure preserving map, which is essentially completely reversible in the sense that no information is lost. And they show that this is good enough for generalization, or if actually generate very well. So this seems like a contradiction to my story. I'll come back to this. And there are other arguments which I'm not going to get into. Okay, I have answers, I think, to most of them, but it's actually quite interesting the amount of, emotions involved in these things. I mean, it's quite amazing. I mean, so people really bother to invent new algorithms to show that I'm wrong. It's really a good sign. Eh? Anyway, so the way I think about neural networks is the following. I mean, so you all know, I already told you that this is a layer of a cascade of transformations. So essentially, think about the variable x as my input, like pixels of an image, if you want that. This is the generic example. It can be many other things. So pixels of an image, you're talking about a 10 megapixel image. There are 100 million bits of variables there. So this is a huge input. And on the other hand, the label, I'm talking about what we call simple supervised learning. So there's one bit, let's say, is it me in the picture or is it not me in the picture, or something like this, which is essentially the label. It can be a few bits. I mean, maybe I classify objects of different types. But usually what I call y, which is the desired label, is a very simple variable. It's a low entropy variable, maybe 1, 2, 3 k bits, and whereas the x is a huge variable. So the entropy of x is a lot larger than the entropy of y. Entropy of y is essentially the number of questions you want to ask. I mean, is it me or not me? 1 bit. The only problem is that this bit is distributed all over the 100 million bits of the image in a way which is very hard to find. I mean, it's nowhere. There's no single bit somewhere that tells me that. Okay, so I have somehow to squeeze out the relevant bits or the relevant information out of these 100 million bits. And what those layers are doing is essentially reshuffling and compressing, in my view, essentially getting rid of all the unnecessary information, the irrelevant information, or the non-informative information, and eventually, layer by layer, generate a representation at the end, which is very easy to decode. Essentially, one hyperplane through my data separates the images with me from the images without me. Okay, so this is some sort of a miracle. I mean, how does it happen? And then the real question is, what happens during this cascade of transformations? Now, I need just to remind you, I hope all of you know, so we're talking about information theoretic measures, which I really want all of you to appreciate. So you all know what the entropy is of a distribution, minus sum of p log p. But so there is a related, very important measure, which we call the cross entropy, or the KL divergence, or the information divergence, or many other things. And this is this D, which is the average log likelihood ratio of two distributions, average with respect to one of them. This is a non-negative quantity, which is some sort of a distance measure between distributions. A direct measure, consequence of this particular function, which is very important for many reasons, which I'm not going to mention, is the mutual information. So the mutual information is how much information there, how much uncertainty is removed about one variable, in our case x, let's say the input, when I know the other one, and I know another variable, and I can write it as a KL divergence or a cross entropy between the joint distribution of two variables and the product of their marginals. So you see that immediately that this is going to be 0 if they're independent. But otherwise, it is actually the difference between the entropy of x and the conditional entropy of x given y, which is exactly this, the uncertainty in x minus the uncertainty of x given y, which is how much is y removing from uncertainty of x. This is an essential quantity in the whole story. So in some sense, this is what is encoded in terms of mutual information, in terms of information quantities, in the picture x about the value y. If this information is not there, there's nothing to learn. Okay. Mutual information has a lot of important features and quantities. It's actually the generator of the main theorems of information theory, which I'm not going to mention. But I need you to remember one thing. There's something called data processing inequality, or DPI, which is essentially if you have a Markov chain of representations, and by the way, I didn't say it, that you see in this layered network that there's a Markov chain of representation. The first layer is a function of the previous one. Each layer is a function of the previous one, unless there's some skipped connection or things like this, but this is not really changing much. So there's a Markov chain of representations there. And if there is a Markov chain, we know that mutual information cannot increase. Information cannot be generated. That's why I call data processing. If you process information, you can only lose information. And essentially, so information between, if there's an XYZ Markov chain, the information between X and Z cannot be larger than the information between X and Y. Okay? So, of course, as an immediate consequence of it is that information is invariant to reparameterization or any permutation, any one-to-one function, which is really bad news because it tells you that the information measures are completely invariant to computational issues. So all the things about the time that it takes to converge are not going to be described by information theoretic measures. Remember that. That's why we need to think about the dynamics. Now, once I know this, there is this immediate chain of inequalities. So that first thing is telling me that the information between the input and each one of the layers is only decaying, and they're all bounded by the entropy of x. And the information about the output, the desired y, and each of these labels is also decaying. So these two chains of inequalities are generating some sort of a path for every network. Okay? And again, very quickly, the way we actually think about it is we think about each layer as characterized by two functions. One is what we call the encoder, which is essentially how the input is mapped into this layer. This is generally a lossy or stochastic map. It doesn't have to be, but it can be. And the other one is what we call the decoder, which is how I decode the output from this layer. So each of this parameterization, each of these layers is completely characterized according to our theory by two numbers, and two numbers only. How much information it remembers about the input and how much information it predicts about the output. Now, this is a huge reduction in complexity. I mean, I'm taking these millions of parameters per layer that we have in these big neural networks and turn them into two numbers only, and I dare say that these are enough to know what we really want to know. In the sense that if I actually give you the mutual information of the encoder and the decoder of the last hidden layer, I'm giving you the optimal trade-off between the sample size, I mean, how much data you need, versus how accurate your prediction is going to be. Or I say it again, I mean, everything that you care about in machine learning, or one of the most, except computational complexity, is how much data you need in order to make a certain prediction, accurate prediction. Or what is the trade-off between accuracy and sample size? And I actually argue that this is completely determined by these two values under some conditions. Yeah, if I'm going to answer questions now, I'm not going to get there very far. So unless it's very urgent, I mean, something that I'm saying is completely wrong or misunderstood.
Okay, so I'm going to throw the question and you can answer it or not. So the reason why you can do like thermodynamical limit is because the type of the interaction in some physical problem give you some equilibrium, which depends on the microscopic stuff. So is it true that for any general interaction you would reach an equilibrium? Or?
Okay, so this analogy is a little bit too crude. I mean, but yes, I'm going to talk about it. Okay, so in some sense, what I'm saying is that these two numbers for a trained network are enough to know everything that you want to know in terms of the quality of the representation. I'm not saying that there's no more there. So just in order to convince you that this is an interesting story, I'm going to show this movie, which I showed many times, but I actually hope to say many things that I haven't said anywhere. So this is essentially what I call the information plan of a neural network. So what you see here on the x-axis is the information that every one of the layers. So T here is T1, T2, T3, one of those hidden layers. So it goes from 1 to 6 in this case, and each color is a different layer. And IT, so ITX is the information between the input and the layer, and ITY is the information between the layer and the desired output. So this is generalization error. Yeah. This is how much I'm going to predict a good label outside of my training data. Now, what you see here is the initial conditions of 100 repetitions, random repetitions of the same layer, the same network. So what we do, we take a certain network which has 6 hidden layers, and we trained it on a certain problem. It doesn't really it's not really important at this point, and we just repeated it 100 times with 100 different initial random Gaussian 0-1 initialization of the weights. And then we train them with different samples selected randomly and different mini batches. I mean, every one of the partitioning of the data is also randomized. So that's why you see this. This is before training, just the initial conditions. And partly starting to answer your question, you see that the layers tend to lie in very specific places in this plane. I mean, so the first hidden layer is here in blue. It's very high because it's very close to the input. So essentially, it's not forgetting anything about the input. So the entropy of the input in this case is 12 bits. Doesn't really matter. And it's also very high with respect to y, which means that it has all the information essentially that the input itself has about y. Now, once you go through the layers, information is lost, and you see this very sharp drop of information. The yellow one is actually the third hidden layer, and then the pink one is the fourth hidden layer, and so on. And the last hidden layer is the orange. And eventually, the already striking feature that even without doing anything, these layers tend to concentrate over in this plane, even over many randomized initial conditions. Now, what I'm going to show you is how these layers are going to behave when we start training it with stochastic gradient descent. And what you see is this type of behavior. Now, when you see this, you immediately think about statistical physics. This I immediately think, because you see these very nice fluctuations of all the points, and eventually they converge in a very interesting way after 10,000 iterations, more or less, to a point where the last hidden layer is actually telling you a lot about the input, but very little about a lot about the output. I'm sorry, about y, but very little about the input. And all the other hidden layers essentially moved somehow to the left and incrementally, and eventually give you a forget. So, and just to make this clear, there is a first phase, more or less up to here, about 300 epochs, where you had a relatively fast improvement in the information about the label, which is what I call generalization, and also some movement to the right, which means that the layers remember more or learn more about the input. And the fact that you see them decreasing from the right top to the left is because of this data processing inequality. So, information can only get lost. But from this point on, which is a very special point in our story, they start to do much slower. I mean, if you look at the number of epochs up there, you see that most of the epochs actually happening, and the main improvement in generalization error happens when they move to the up and to the left again. And eventually, you get trajectories which look something like this. I mean, essentially, this is the average. You get from A to C very, very quickly. This is what I call the fitting or drift phase of the problem. And then from C to E, all the layers essentially get to this point of maximum information about the input, and then they slowly move along these interesting contours to the left and improve generalization. So actually, this picture was some sort of an X-ray of the black box of deep neural networks, because so far we didn't really understand what's going on there. This information theoretic view actually gave us some insight about what's going on in the network. Now, it's not only a visualization technique, which of course many people are intrigued by, and so what we did here is estimated this information numerically in some way, which can be criticized and should be criticized because it has all sorts of arbitrary things like binning the weights and binning the values of the neurons and so on. But this is not the important part. The important part is really this type of trajectories. I mean, what's really happening here? And I just want to emphasize again the question. So is this a general quick picture? I mean, do we see this for other problems? Yes, the answer is yes. Do we see this for larger problems? Not only we see this for larger problems, the larger the problem, the more concentrated these points are. So essentially, what makes those mutual information values concentrate so nicely in this plane? I mean, this is precisely the answer to your question. Why are these good order parameters? Is there some sort of equilibrium here, which I can talk about? And I claim, yes, there is. There's a very nice self-averaging of these quantities under some very mild assumptions about the distribution. What do these numbers mean? I already told you that the main interpretation of the theorems that we can prove, and I'm not going to prove here, is that the first number, the information about y, is giving us a rigorous bound on the generalization error, no matter how we measure it. With any reasonable measure of the error, more information is smaller error. It's actually a very sensitive bound. It's an upper bound to all those standard generalization errors. Actually related to the cross-entropy training error that we use in practice in many cases. The other number, the information about x, I argue, is actually controlling the number of examples we need, the minimal number of examples we need in order to achieve this generalization. So actually, it's some sort of a min-max bound. It's the minimum in the worst case, and it's exactly what we need. So this information about t, about the input, is telling me eventually the sample complexity of the problem. So this is something I'm arguing, and I'm talking much more about when I talk to computer scientists. I'm not in the mood right now to actually tell you this, just because I think this is the less interesting part of the story, and you can find it on YouTube and various places. I just want to emphasize what is my assumptions here. So essentially, when I say that I'm talking about typical problem, we're using this particular property that is used known in information theory as the Shannon-Macmillan bound, or limit, which is essentially, if I take the log of the probability of many variables, in this case, the pixels of an image, for example. So there are a million pixels of an image, and I want to know what is the probability of an image, one image. And I'm telling you that under some very mild assumption, for example, that the probability of the color of a pixel is almost completely determined by the pixels around it. So there's some neighborhood of the pixel where I know, if its colors, I can predict the probability of the color of the pixel. This sounds very natural for images. And it's actually true for Markov fields, random Markov fields, from hidden Markov models, for Hamiltonians with finite degree of interaction, for what we call graphical models with finite average degree of the graph, and so on and so forth. There are many, many statistical models, including all those that we like in physics, pairwise interactions and things like this with short-range interactions and all these kind of things. They're all of that type, which means that the distribution of the data is factorizable localized. So I can write this log probability, or this probability, as a product of many conditionally independent terms. And then the log of it looks like a sum of conditionally independent terms, and then the central limit theorem applies, and these things tend to average. This is really the heart of the success of information theory and also of statistical mechanics. So essentially, the fact that large problems tend to concentrate in things like the log probability. Now, of course, it's true for the Gibbs distribution, many other things. This value to which this limit approach is the entropy, essentially, of the source. And when I talk about only typical patterns, I talk only about the things for which the probability is essentially 2 to the minus entropy, with this factor n, which eventually I suppress. So all the typical patterns are, first of all, most of the patterns are typical, because take an epsilon away from age, you capture essentially everything, because it's a very sharp distribution. And not only they are typical, they have the same probability, which is 1 over 2 to the minus nh. So this actually, and actually assume that each of the layers is actually partitioning my data into cells. So if you can think about the neurons as just discretized neurons, or 0, 1 neurons, something like this, then each layer is inducing some sort of a partition of the input. And conditioned on this partition, I assume that the patterns within this partition are also typical, in the sense that their probability is exponential in the conditional entropy. Okay, so these are the two assumptions I'm making. I'm talking about typical patterns, and I'm talking about conditionally typical patterns. These are, by the way, the same assumptions that are used by Shannon in his coding theorems. Now, under this assumption, first of all, I can show that indeed these two quantities, the information about the input, the information about the label, self-average. And this is something I dare to show onto the physicists, but because it's a little complicated, but you see there that these products tend into sums, and these sums tend to average, because they are sum of independent terms, conditional independent terms. And it's true both for the information about the input and about the information about the label. Actually, about the label is a bit more tricky, but it's for the same reason that the log partition function in statistical physics is the thing that tend to average. That's why we average the log partition function and not the partition function when we do calculations in disordered systems. So for the same reason exactly, these two quantities are sharp. And that's why you see this very nice concentration in this information plan. Now, this actually gives me this very interesting bound, because knowing that they are typical, I can actually move from the classical information sample complexity bounds, which are on the left there, which essentially tell me that generalization error is bounded by the log cardinality of the hypothesis class divided by number of examples, essentially, and where this goes like the dimension of the space, the VC dimension or the Hausdorff dimension of the hypothesis class divided by m. This is the classical bound. I'm actually moving it to an entirely different type of bound. This is this 90-degree rotation. Instead of being problem independent, but class very strongly expressivity or hypothesis class dependent, I throw away all these expressivity results. I don't care about them, because these bounds don't work for deep learning. They miss by orders of magnitude in prediction of generalization error. I twist it to a bound which depends only on the mutual information between the layers and the input. And this particular compression is quite impressive, because essentially every bit that I managed to compress my representation, which in this video is this motion to the left of the layers, is equivalent to a factor of 2 more data. So if I manage to compress it by 6 bit, it's essentially like multiplying the size of my training data by 32, or by 64, sorry. So this is a huge factor, this exponential dependence. And this exponential dependence is very different from the linear dependence in dimension that you get in the classical bound. So I dare to say here that all those expressivity results that show you that deep neural networks can express very complicated functions are essentially irrelevant for this argument. It doesn't explain what we see in those experiments. The neural networks are doing far better than what we can expect from the bound on the left. Okay, so now, in a sense, now the interesting question is if they really compress the representation in this plan, is there a limit in this plan beyond which no neural network can go, or no representation can go? And the answer to this is interesting, because it goes back to a very old work of ours, which we call the information bottleneck problem. So this was actually motivated by an attempt to characterize minimal sufficient statistics. And as you know, physics is full of those things. I mean, energy, entropy, momentum, angular momentum, whatever, any good observable of many particle system in physics is a good sufficient statistic in the sense that if I know its quantity or its average, I can tell you a lot about the system, essentially everything I want to know. So minimal sufficient statistics are important, and they are completely characterized by a variational problem, which is this one. Minimize the mutual information that given the statistics, subject to the constraint on what you know or what you care about. And if maybe the parameter of the problem, maybe the temperature, maybe the energy. I mean, it can be many things in physics. So this is essentially this type of variational problem, which is this Lagrangian. I mean, minimize the information about the representation subject to a constraint about the information on the output. And beta is a Lagrange multiplier here. This is for physicists, this is a very simple and very clearly similar to the trade-off between energy and entropy in thermodynamics, and this looks very much like, and beta indeed looks like inverse temperature. So in this case, the energy is something like the information about the label, and the entropy is the information about the input. So this analogy works perfectly, so I call it free energy in most cases, and that's what we mean by that. And essentially, analyzing this problem as a function of beta, as a function of temperature, is giving us some very exciting story, but it's also giving us a bound. So we can actually solve this problem. If we know the joint distribution of the input and the output, the solution of this variational problem is amount to these three equations, or actually two equations, which I need to iterate. One of them is the equation for the optimal encoder, which turns out to be exponential in the cross entropy or DKL between how well I predict the data from the label from the data versus how well I predict the label from the representation. And now, so this is what I call the optimal information bottleneck encoder. And this is associated with this red equation, which is the optimal information bottleneck decoder. And in order to solve the problem, we actually iterate these two. So we start with some initial encoder, plug it here, plug it, and essentially iterate these two equations. And then you get this very interesting line, the black line in this curve, which is, in information theory, it's known as a rate distortion function, but it's actually telling me what is the optimal trade-off between remembering the data versus predicting the label. And so this line is an information theoretic bound in the sense that nothing can go beyond it. There's no algorithm or no hypothesis class or no alien out of space who can get representation from this data above this line. Now, so this line is the optimal you can do. Now I can calculate this line for every given problem. If you give me the joint distribution of x and y, or you invent it for me, which is, by the way, is equivalent to giving me the Hamiltonian of the system, or something like this, then I can calculate this line. And this line has this very peculiar property, so it's a downward concave line. The derivative is 1 over beta, as you can expect. And it has those lines, the blue lines, which are a cascade of phase transitions, or if you want, topological changes of the representation, which I can predict from those equations. So they're all data dependent, they're algorithm independent. So given the data, given the joint distribution of the data, or even a sample of it, I can calculate this line to some accuracy, the black line, and I can also calculate where exactly in beta there are going to be changes in the topology of the representation. I'm going to come back to this topology shift eventually. What is important to emphasize is that if you are given finite data, you're given just a sample of your problem, then you can't achieve the black line theoretically. What you can achieve is only the red line. And as you see, the red line is very different from the black line. It's actually very different at the end, at the right end, where I need a lot more details in my representation than I actually have data to support. This actually means, let's think about the first hidden layer. This is like a random hyperplane thrown at my data. I have a lot of small partitions of my space without any label. So I cannot predict anything from that, and I get a big drop of the prediction power of the information. On the other hand, if I compress too much, I have a very coarse partition of my data. I cannot get anything out of it, even if I have a lot of data. So there's somewhere right here, some sort of a maximum of this red line, which is the best you can do with finite data. Of course, everything is exaggerated in this page, in this particular plot, just to make the point. In reality, the black line is a lot closer to the top of the picture, as you saw before. And the red line is actually getting closer, and the more data I get, the higher this red maximum is and closer it is to the line. So essentially, when we train a network, we really care about minimizing two terms. What I call the compression loss, which is how much I lose by compressing the representation, and what I call the finite sample loss, which is how much I lose because I have a finite sample. And therefore, my argument is that somehow stochastic gradient descent is pushing the network into this region of the maximum of the red curve. And that's why they're so good. Not only that, I actually argue they have enough data, all the layers of the network are pushed to the black line, eventually. So this is a very strong argument, and I need to support it with some data. So essentially, this is just to give you a big picture for a second. So these plots up there are essentially the same plots I showed you before, but the color here is the number of epochs. Okay, so purple is a very small number of epochs, and yellow is very large number of epochs. And what you see is how this dynamics again moves through the layers. You see the same type of trajectory contours that I showed before, and you see that most of the time are actually stuck there at the end, and eventually the layers end at some points, these yellow points, where they get stuck. And actually this is interesting. But what is interesting in this picture is that I trained the network with different number of examples. So on the right, you see trained with a lot of data, in this case 8% of the data, and then on the left you see, I'm sorry, what is this? This is silly, I get a phone call in the middle of a talk, but I don't see my slides anymore. This never happened to me before. This is Siri. Oh, okay, yeah, okay, sorry. So essentially, you see this on the left here. You see the same thing with 5% of the data. And what is really interesting is that the first part of the plot, I mean, coming all the way to this green line, and remember, this green line is where I remember the most about the input, and then I start to forget. So this is this type of phase transition between remembering and forgetting. This happens essentially in the same way, even with very small data. But the second part, where I actually compress the representation when I forget the details of the input, are very different. In the first part, I actually keep improving the information about the label, and in the last part, I actually get down, which means that I'm over-compressing. In some sense, I'm overfitting. This is very much like overfitting, which you're all used to, but it's actually not overfitting in the sense that I'm not fitting a more complicated function than I can. Actually compressing or simplifying the representation, but I compress without support of labels. So I get very few labels, not enough to actually make good predictions. And that's why early stopping or something like this, I mean, don't train too much, is going to help us on the left. Okay, and actually claim that all the lines to which the layers converge to, I mean, both with the large sample and with the small samples, are predictable, are properties of the distribution of the problem only, and not the algorithm. So this is, again, algorithm-independent results. So now the question is, what's actually happened here? Why are the SGDs so effective in compressing the representation to this optimal bound? So indeed, if the layers indeed reach this black line, or saturate this black line, they are optimal learning machine. Nothing can do better. It's something we would like to know, if it's true. Or when is it true? Now, because if this is the optimal, we don't have to work so hard trying to improve this aspect of them. We want to improve other aspects of them. And that's maybe why they work so well. So, of course, any thinking about it will tell you, you must see this in the gradients themselves. And what is the property of the gradient, of the stochastic gradient descent, which is actually pushing this representation to this information theoretic limit. So if you look at the training error, or actually generalization error in this case, together with the movie that I showed you before, so the line there is the error, my prediction error of how well I fit the data. You see it starts from 0.5, which is random prediction, and then eventually, at some point, there is a knee a very sharp change in the derivative in this curve, which happens around 300 epochs in this case. And exactly at this knee, my information plan movies started to move from moving to the left to moving to the right to moving to the left. So this was a very clear indication that there is a property of the gradients of the error which is changing at this point. And indeed what we did next is simply plotting. So this is my neural network. It's a very simple neural network. It's too simple. And of course, you want to know that this is not working only for that. So we checked that. I don't have time to give you all the examples. But we have many, many different layers, networks with very different types of nonlinearities, including ReLUs, and very different types of connectivity, including convolutions and including any other trick including regularization. We always see this type of picture. And this type of picture is in the gradient is actually quite interesting. So what you see here in different colors is the average gradient per weight in every one of the layers. So the red is the first hidden layer, then other colors are the other layers, and the purple is the last one. And you see in the broken line the standard deviation of those gradients, and I can measure them in two different ways, either across the batches, the mini batches. So the mini batches are generating some sort of the distribution of gradients. Actually, we recently showed that you can calculate it in time. I mean, essentially comparing the gradients in two consecutive updates of the weights. And these are the update to update fluctuations. And what you see there is the trace of the covariance matrix, just to be invariant to transformations or whatever. 10 minutes, wow. Okay, so essentially, this is what happens here. There is a high signal-to-noise ratio, which is very clean gradient at the beginning. And then when the error saturates, you move to a low signal-to-noise ratio, which is where the variance or the standard deviation is much higher than the mean. And essentially, this is converging to this saturation, and actually the details of the gradients are sufficiently enough to calculate from the gradients the information contour using the Fokker-Planck equation. So this is quite interesting. I don't need to do any measurement of information. I can just look at the gradients, plug the covariance matrix into the diffusion term of the Fokker-Planck, and plug the drift into the drift phase of the Fokker-Planck, and you get the same evolution of information. So, okay, so this is why I argue that you really don't need to calculate too much. Essentially, the story is, again, very, very simple once you understand it. The weights, the gradients have very large covariance matrix, but very skewed. Most of the dimensions of the weights are irrelevant. So out of those million or 10 millions or whatever dimensions of the weights per layer, it's order 10 features which are really important. Let's say face recognition problem. What do I really care about? So the distance between my eyes, the ratio to eyes to nose, or whatever, some geometric features of my face. These are very few number of parameters. There's a huge space out there of weights, which is completely indifferent to the error. So what happens is that the gradient have a huge variance in most of the dimension, which I call the irrelevant noise, and very small variance in all the dimensions which are affecting the error. So essentially, the weights are going to converge eventually to the optimal weights, which I call the canonical correlation analysis weights, for reasons which you can read on, but I don't have time to describe. So this is the optimal projection if I could train it infinite times, and I get to this. But in addition, they have this delta W, which is essentially a noise, a random walk type of measure. So in all of the irrelevant dimension, I do a random walk, so I get something which grows like square root of t in size. But otherwise, square root of number of updates. But otherwise, it's very, very wide in the irrelevant dimension. It's very narrow in the essentially with this covariance matrix. Now, when you work with the network, you multiply the previous layer by those weights, and then follow by this nonlinearity, which I call here sigma. So the information, the layer-to-layer information, is bounded by the capacity of the Gaussian channel, which is described by W times T plus delta W times T, which is essentially noise, because this is a big random matrix multiplied by a big random vector. So this looks like a random vector unless you really track the details to infinite precision. So it acts like noise. When it acts like noise, to any precision, the information, layer-to-layer information, is bounded by the log of the signal-to-noise ratio in this component. So this is the essence of the story. the diffusion, the slow diffusion that the gradients are making in the irrelevant dimensions is compressing or forgetting the irrelevant details of the problem in all the irrelevant dimensions. And this happens without anyone telling me what is relevant and what is not relevant. It happens just by the stochastic nature of the gradient. Okay, so now I can talk about the interesting part when I have no time. So essentially, what we argue is that all the layers eventually converge to this optimal information theoretic bound. That's in this particular example, that's what you see. And you see that each layer is this red cross. This is spread over these 100 repetitions that I showed you before. You see that the red cross are amazingly close to the theoretical bound, which is the blue line, which I can calculate. Not only that, each one of them has a different value of beta. So now you can ask yourself, okay, what determines, so it's not a Gibbs distribution, it's a Gibbs, or it's locally Gibbs, a different temperature for different layers. So anybody who is telling you, and there are some people who do that the whole network is converging to a Gibbs distribution, I think this is completely wrong. It's some very special type of Gibbs distribution, which is a result of this Langevin dynamics, and Langevin dynamics approaches Gibbs distribution eventually, but since the noise is highly non-isotropic and is state dependent, the temperature is actually different from different layers. But the really interesting story, okay, so in that sense, at least neural networks are optimal. Not only that, they're forming something which we call the irreducible representation. It's essentially the sum of the errors between layer to layer is exactly the error of the last layer. So this is somewhat peculiar, which means that's why we call it successfully refinable problem. Essentially, every layer is compressing, all the layers lie on this optimal curve. And if I think how much I lost in every layer, the sum of all these losses measured in information is precisely, to a very good approximation, numerically at least, and the error from the beginning to the end. So the blue line is the sum of the green lines. Now this is interesting because it's actually telling us each of these representations in some sense compressing as much as it can. And the really interesting question is, where do they stop? And so first of all, there is a very interesting prediction out of it, which is why the layers really help you. So first of all, you see again the dynamics. I mean, this is the same problem trained with one hidden layer and 2 and 3 up to 6 hidden layers. And if you look at the colors, just impressed from the color, in the first one, although I can learn the rule, it takes forever. Essentially, in the high yellow there, I still don't converge to a good solution. Whereas the 6 hidden layers, a lot larger problem, many more parameters, I converge much faster. This is with the same epoch size, the same mini batch size, so the number of epochs is the right thing to do. Now, this requires explanation, and in this diffusion theory, once I understand that what governs the time is the time of expanding the entropy in diffusion, and you know, diffusion grows like a Gaussian with square root of t width. So essentially, if it's unconstrained, so essentially the entropy grows as exponential in the time, is logarithmic in the time, because it's the log of the standard deviation. So the time is exponential in the entropy increase. And this tells us that we have a very highly, strongly nonlinear improvement, actually exponential improvement, when I add layers in terms of time. So this begins to be a computational theory which comes from the properties of diffusion. So this is a very exciting problem for statistical physicists. But the real exciting problem is what happens to the topology of the representation. So this is the topology, the two-dimensional scaling of the first hidden layer. The first hidden layer. And what you see here, black is where the network is labeling the data by 1, and red is where the labeling is 0. And the stronger the color, the more confident the network is. And what you see here is how the topology is organized during the training. And you see that you get this salt and pepper mixture. I mean, red attracts red indeed, and black attracts black, but the topology is still highly mixed. And this is a very simple problem. Imagine what happens in complicated problems. So this topology, the first hidden layer cannot in any way linearly separate the data. Now what happens if I look at the same thing at the fourth hidden layer in this particular problem? So you see that it starts with some sort of asymmetry between black and red, but eventually again during the training, something completely different happened. All the reds move to the right and all the black move to the left. And actually you even see that the dimensionality is reduced. Everything is collapsed to one dimension event. Now, this is a very intriguing question from a statistical mechanics point of view, which is essentially telling us, okay, so first of all, this is a reassuring, it's completely consistent with what I told you before. The irrelevant dimensions are eliminated from the problem by the noise. But it's not only that, it's telling us that there is a topological phase transition that change the topology. Things which used to be close in the beginning are far away at the end. Otherwise, you cannot learn it. Now, topology phase transitions are associated with the phase transitions of the bottleneck problem. And that's really interesting, but that's the beginning of another talk. Okay, so first of all, what you see here are those information about the input, information about the output, but as a function of beta, the temperature. And for any physicist, these cusps, I mean, this continuous derivative means that there is a phase transition. I mean, this is a second order transition because it's a discontinuity of the derivative of the derivative. Okay, so along the information curve, there are all those second order transitions of the problem. And now, because I believe that there is a match between where the layers are and where the bottleneck problem is, I can predict the structure of the layers simply by studying the phase transitions of the information bubble. And that's exactly what we do. So we actually give a concrete prediction where the layers are going to end because they must lie in different topological phases. And they lie in different topological phases because I showed you that the topology is changing. Topology changes only in these phase transitions. I know exactly how it changes. It actually changes according to some sort of bifurcation theory, which I'm not going to analyze here. But eventually what we get is that there is a tree of splits of these phase transitions, which is as a function of the information about the input. The closer I am to the input, the more splits or more phase transition I have to have. At the end, it's a binary question. I have to ask only yes, one question. Am I to the left or right or some hyperplane? This is why the topology is simple there. At the beginning, there are many questions. Now I can tell you that so the theory predicts not only the structure of the phase transition, but that the weights are going to be related to some sum of eigenvectors of this stability matrix, which are exactly the hyperplanes that tell me if I'm the right or left of every one of those splits. So this is a very detailed prediction. I mean, not only I'm telling you where the layers are going to be in the plane, they're going to be determined by the phase transition, but what the weights are going to be, at least up to some linear transformation. And that's exactly what we see now in this simple problem. And that's why we actually took this simple problem, because it has a very specific symmetry. And where there is symmetry in the data, for example, in this case, there's O3 symmetry to the data, which means that rotation of the pattern is not affecting my label. Then these phase transitions are very simple. This looks very much like atomic physics. I mean, group theory is telling you the whole structure of the split. So this is why I really was excited to talk about this since a physicist, but I need another hour to actually explain all these things. So I think I'll stop here and just keep you curious. Okay. So essentially, we show that the information theoretic view is giving us, first of all, unique visualization, but they actually show us that the layers converge to some special points on the IB curve, which are those critical transitions. And there are actually good dynamic reasons. You know that diffusion is actually slowed down by phase transitions. I mean, this you all know, I hope. Some what you call critical slowing down. So essentially, phase transitions in this plane are going to slow the diffusion, and that's maybe why we get these layers stuck at some places. They don't move beyond some places because there's a free energy wall, which is usually mostly an entropy wall, entropy barrier, which is obstructing this diffusion. So there's a very interesting relationship between the dynamical property of SGD and the phase diagram of this trade-off, this free energy landscape, which is turned out to be very predictable, very predictive. I mean, I can predict a lot of details about the problem and eventually also improve the algorithms, but that's a different story. So there are many other things to do. And of course, I'm here today and tomorrow. And if you have any other burning question, always mail me or call me. Thank you.
Suppose that the network were literally representing a statistical system, in the sense that, say, the inputs would be...
Boltzmann machine or something like that.
Well, I had in mind just any neural network, but
right.
the input would be like field configurations of some statistical model, and the output would be the state variable. Would there be any relationship between the thermodynamic the analogous, what am I saying here? The statistical physics analogy that you've constructed here and the physical statistical mechanics of the system you represent?
Well, it's a very good question. I don't have a complete answer to this. It's just that, yes, I mean, the analogies go... This is a special statistical physics problem. I mean, it's not the one you're used to, but it has all the properties of statistical physics. I mean, there are phase transitions, there are criticals, there are latent heats, there are all those discontinuities in the representation. It has all the formal structure of statistical mechanics. Whether it actually corresponds to a real, what you call real physical system, is something which I'm not sure I know how to answer. I can construct a physical system for any joint distribution of x and y. So image processing, or image recognition, or face recognition, or I don't know, high energy physics experiment, whatever it is that you care about, have some joint distribution. There are universal classes of problems. For example, I'm telling you that all the problem which has explicit symmetry underneath, and you give me the group, the symmetry group you care about, has a very explicit structure of phase transitions, which can be predicted and are going to be essentially the structures that those layers eventually find. So I don't care whether you actually map it to a real physical system, but I'm telling you that your knowledge of physics is very useful in analyzing these particular systems, and there is enough, there are enough of them out there that we have to understood. Yeah. So, okay, that's partial answer to your question, but that's all I can tell. I think it's a good question. Okay, so I'm still here.
More questions?
Yeah, I think people are either overwhelmed or tired. But yeah.
Is it possible to translate some of your results into statements about the geography of that landscape on which you do the...
Yes. Yes, okay, that's a very good question. I'm sorry, each question is immediately going to trigger a long answer unless the chairman cuts me. But yeah, so as I said already, I mean, this is we know quite a lot about the landscape of the free energy. It's in this type of picture. And the landscape is essentially below the red line or very down. You're in a phase, in a gaseous phase, ideal gas. There's no structure. I mean, there's no obstacle to movement, to diffusion. It's completely open. Once you get close to the phase, to the line, those phase boundaries, the blue lines, start it's something like a wall, which is getting higher and higher of free energy. So crossing the blue lines is harder for diffusion. And that's why I believe that the layers are eventually funneled through these base phase boundaries and end up at the phase transition. That's at least my prediction. Now, in a real problem, there are many phase transitions. There's a zoo of bifurcations like this, and this is why it's harder to learn problems. There's a lot of phase transitions, but they're all relatively minor free energy barriers. So it's a complex. In symmetric problems, there are very few phase transitions because they correspond to some properties of symmetry group. And those are easier to learn because those tunnels are much wider and diffusion finds them material. So there are many predictions like this which we can make, but this is again just to tease you. Yes, please.
So you haven't mentioned the word renormalization at any point during the talk, or
no.
Renormalization group. Is there anything that you know from that approach, theoretically useful for describing these phase transitions?
Well, it's again a very good question, but so actually it was the paper of David Schwab and Mehta and Schwab that triggered my thinking about this. But I really don't think that typically the renormalization group is a good description of what's going on in these layers, because you are not approaching in any sense a fixed point of anything. Because unless you are talking about self-similar, where there's complete line scaling, and there are problems like this. There are problems in nature like this, but it's not the typical problem. Now, so there's something else which happens between the layers, which is not precisely the renormalization group. But of course, now, so this is just about the big picture if you talk about the Mehta and Schwab paper. But on the other hand, I'm telling you that there are many phase transitions that are affecting the behavior and the convergence of the layers. Each one of them can be analyzed using renormalization, if you want. I'm not sure it's an interesting problem on its own, but I'm sure that the way the dynamical properties of the convergence are affected by the free energy structure, which can be explored using renormalization group. So actually, a long time ago, I worked on anomalous diffusion and diffusion near critical points in the nonlinear dynamics, and that's why I actually got this intuition that eventually diffusion slows down near critical point. This, of course, known. Not only slowing down, the exponent goes from 2 to much lower. So there is this sluggish diffusion which people actually report in machine learning without really understanding what they talk about, of ultra slow diffusion or ultra slow convergence and many other things, which I believe have to do with topology change or phase transitions in the problem. This is all open, wide open for research.
Let's keep asking Tally questions downstairs during the refreshments. Let's thank him again.
All right, thank you very much.